Hi, I'm Álvaro García López from the Department of Applied Physics in University Rey Juan Carlos in Madrid, and I'm going to talk about the Lorenz system as a thermodynamic engine. Okay. So, just to give three motivations to the present investigation, we would like to start with the concept of dissipative structure, which was coined by Ilya Prigogine, the Nobel Prize winner, a physical chemist, and he coined this concept to define physical systems that are open and they exchange matter and energy with their environment, and because they dissipate energy in terms of heat, they are also called dissipative structures, and they generate entropy. So this opposes to conservative dynamical systems, which are endowed with a symplectic structure. The main question we want to address is if there exists a thermodynamic property that guides the evolution and self-organization of dissipative structures into increasingly complex systems. The second important result, was derived by Leon Chua in 2005. He published it in the International Journal of Bifurcation and Chaos, and he established the sufficient and necessary conditions for dissipative structures to display a coherent and nonlinear stable dynamical motion. Ordered dynamics, I mean nonlinear self-sustained oscillations. Basically, this condition is that the systems are active, and by active we mean that they are capable of amplifying energy fluctuations from the environment and convert them into coherent motion. This involves symmetry breaking, and when you have active and stable dynamics in a system, you can have all type of complex dynamics, pattern formation, nonlinear waves, oscillators, and all the interesting dynamical behavior. So, of excitable systems. So finally, the third concept, with the third vertex of this triangle, is the concept of self-oscillation. The self-oscillation is basically the production of periodic motion by using an external energy source, a gradient of energy in the environment, without periodicity. So the system, with its motion, the stationary state can destabilize, and with its motion it manages the way in which it takes the energy. So there is a constant feedback between the source and the dynamics of the system. These are called also self-sustained oscillations by Alexander Andronov in his book of nonlinear oscillations. The key point that has been addressed by Alejandro Jenkins here in his physics reports, with a lovely historical introduction to the concept of self-oscillation, is that self-oscillators behave like thermodynamic engines. They have a thermodynamic structure that was pointed out by French engineer Le Corbusier in the 1930s. So this is the crucial idea that we are going to use. And to be very specific, we are going to use a system which we believe it's quite universal, and at the same time is very well known. So we have empirical results, experimental data. This is the Rayleigh-Bénard convection. As you all know, when you have a fluid, you hit it from below and it's in the gravitational field, and at some point, if the temperature is high enough, then the temperature gradient induces the symmetry breaking of the fluid, and it starts to perform coherent convective motion. And this motion, of course, are the convective rolls, which are limit cycles. And what has been shown experimentally, and you can find these results in this paper, is that as you increase the energy gradient from the environment, which is represented by the Rayleigh number here, the total heat flow through the dissipative structure, which is related to the work performed in these limit cycles, increases as well. And this also happens for the rate of entropy generation in the system. So we want to know if this happens in the Lorenz system as well. And to study this in detail, we have used a much simpler system than Rayleigh-Bénard convection, which is in fact finite dimensional from a dynamical point of view, and it's the Malthus-Lorenz water wheel. This is a water wheel designed by William Malthus in the 1970s. He was a friend of Lorenz at the MIT. So basically you pour water through the hose with high potential energy. This fills the buckets, and as the buckets become full of water, the wheel starts to rotate. But there's also a leakage of water through the holes at the bottom of the buckets. So you can see this as a living organism. It eats water, it excretes water with less potential energy, and there is also to ensure stability. There is a dissipation mechanism. Otherwise, the system would be continuously accelerating, and the speed would be unbounded. So this is the most modern version of the water wheel, but it's equivalent to this medieval version, and here you can control all the input and output parameters. Well, the good thing is that if you Fourier analyze the mass distribution along the rim of the wheel, you can, these are the first Fourier modes, the odd and the even Fourier modes, A1 and B1, and also you have the second Newton law, which gives an integral differential equation, but the integral differential equation reduces to a three-dimensional system. So what you have here, what we see here is that there is a water income rate into the even mode of the Fourier first mode of the wheel. There is also water outcome which is proportional to mass distribution according to Hagen-Poiseuille's outflow, and then there is friction in the rotation of the wheel, and this is the torque which produces the gravitational field, and that generates the rotation of the wheel, but only couples to the first mode. This is the amazing thing, and then you have the coupling between the rotational speed and the modes of the wheel. So these are three-dimensional dynamical system. As you can see, you can non-dimensionalize it and use two non-dimensional parameters, the Rayleigh number and the Prandtl number. Here I'm going to talk only about the Rayleigh number, and as you can see, it's the quotient between the rate of income of water and the rate of outcome of water squared, and also the dissipation. So the dynamics, if the system is posed far from equilibrium, is a chaotic attractor, which you all know is the Lorenz strange attractor, which displays chaotic dynamics. So we are going to study the thermodynamic efficiency in three regimes. Here I've plotted the bifurcation diagram of the rotational speed of the wheel for different values of the Rayleigh number. So this, if you want, is the rate of income of water, how fast the system is being fed. So when the water income is very small, the wheel doesn't move. The asymptotic state is stationary, no rotation. Okay, so the dead passive stationary state. But as the rate of income increases, there is a bifurcation, which is a pitchfork bifurcation, and then two arms are born, and each of these two arms represents clockwise and counterclockwise rotation of the wheel. The stationary state destabilizes, and you have symmetry breaking of the reflectional symmetry of the wheel, and one of the two rotational modes is settled. And if you keep even feeding more and more the water wheel, at some point the dynamics becomes chaotic, and you have both clockwise and counterclockwise rotational speeds, and these alternate in an unpredictable manner. So there are basically, these two are active dynamical regimes. So here you have symmetry breaking, here you have symmetry restoring in the system. And what we have, our contribution mainly is to compute the thermodynamic efficiency. It's not really hard, but you have to be careful. So basically you are feeding the wheel with high potential energy water. You have a rate of potential energy income in terms of mass, and an outcome as well through the holes, and finally the wheel gets producing work. So basically the thermodynamic efficiency is the quotient between this rate of work production and the rate of energy income, and all this work finally is dissipated in terms of heat into a system. The ideal situation would be to have 100% efficiency with no output, all converted to work, but this is impossible, and this is Carnot's theorem, and there is a maximum value that the system can have. And if you renormalize the thermodynamic efficiency through this maximum, you get this beautiful, lovely formula, which is nothing else than Carnot's equation for the heat engine, but now for a water-driven engine. And the Rayleigh number, just to recall, was the quotient. Instead of having the quotient of temperatures of the thermal focuses, you have the quotient between the rate of water income and the rate of water outcome, and here is the dissipation. So the interesting thing is that if you plot the thermodynamic efficiency as you pose the system farther and farther from equilibrium, the first region you have no motion, so there is no efficiency, but then it starts to increase so fast. okay, towards its maximum. And when the chaotic dynamics settle through the Hopf subcritical bifurcation, there's a drop, sudden drop, discontinuous jump in the thermodynamic efficiency, and then it keeps increasing again. So except for this transition, the thermodynamic efficiency always is monotonically increasing. And here in the middle, what happens is that you have a phase transition. So if you think of Rayleigh-Bénard convection, when you have convective rolls, you're having a crystal. To some extent we could say that as you transition to turbulent regime, the crystal melts. So basically at phase transitions, which are just bifurcation phenomena, what you get is a jump in discontinuity in the thermodynamic properties. But another interesting fact is that here there are periodic windows within the chaotic sea, if you want, and the thermodynamic efficiency keeps increasing, so this means chaos is not necessarily bad for thermodynamic efficiency. What really matters, we have addressed this, is the average size of the limit cycle attractor, whether strange or periodic. To conclude, we have also checked that the entropy generation is positively correlated at all events for all the parameter values of the system with the thermodynamic efficiency. So as you keep increasing the rate of income of water into the wheel, the entropy generation increases. Now it increases linearly. It is a linear tendency. There is a jump again in the entropy generation, and then it keeps increasing. So basically this means that the thermodynamic efficiency is also can be interpreted as entropy regeneration in the universe. And we believe that it's better to check thermodynamic efficiency, which is more easy to understand than entropy generation. So this was all stated already, phrased in clear words by Ludwig Boltzmann, but we have given it a mathematical rigorous treatment. And it's that the struggle for existence, the evolution through Darwinian selection of complex systems into increasingly more complex networks and synchronized nonlinear oscillators, that's what systems are in nature, is guided not only by matter and heat and energy, but it's a struggle for entropy. And this is perfectly clear in our analysis, and we would like to say that the key parameter driving Darwinian evolution and complexity is thermodynamic efficiency. That's our proposal, and that's mainly our idea. So that's how the clocks work, by fitting them. And thank you very much for listening to this talk, and I will very, very happily answer to any questions that you may have. Thank you very much.